Okay, so let's talk about kind of vectors and unit vectors. Imagine that I have a unit vector that looks like that. It's pretty straightforward that it has a magnitude in the x direction and it has a magnitude in the y direction, or it has an x and y position. But this vector could also have a velocity. It could be moving. Suppose a few seconds later it's over here. Okay, so that would be r at t equals 0, and this is r at t equals 2 seconds. So suppose, it's lousy, but suppose it's moving. So we can write any vector is written of the form r is equal to x0 I hat, y0 j hat, plus v0 in the x direction I hat, plus v0 in the y direction j hat, plus 1/2 a in the x direction t squared, plus 1/2 a in the y direction t squared. So for example, if I had a vector of the form, or I had a vector that said r is equal to 3 meters I hat plus 2 meters j hat plus 3.5 meters per second times t I hat plus 4 meters per second times t j hat plus 5 meters per second t squared I hat plus 3 meters per second squared, this should be meters per second squared, t squared j hat. I could begin to assign numbers to all of this. Well, remember that in general, things are relatively straightforward. That's 3 is its initial position in the x direction. 3.5 is its initial velocity in the x direction. But the one that we've got to be careful about is this term right here, 5 meters per second squared. T squared is the acceleration. And going back up and looking at what we wrote here, what we're saying is that 1/2 a in the x direction t squared is in this case 5 meters per second squared t squared. And so that what we see here, and we actually know this from calculus, but if we just want to just assume we don't know any calculus, that this would tell us that a in the x direction is actually equal to 10 meters per second squared. And we know that if we were to take the derivative of acceleration, we would get velocity. The derivative of 1/2 ax t squared is just ax. But we don't know that. So what we should do is we should now try to write at least x or y as a function of t. And so let's do the following. X as a function of t is equal to 3 meters plus 3.5 meters per second t plus 5 meters per second squared t squared. That was relatively straightforward, but that the velocity in the x direction as a function of time would look like 3.5 meters per second plus 10 meters per second squared times t. And again, remember this term is what we figured out up above. The last thing that bears repeating is that at any point the magnitude of the vector, or of the length vector, looks like r sub x squared, r sub y squared, And you can similarly write the magnitude of the velocity is equal to vx squared plus vy squared.